Okay, everybody, let's start with the proceedings. See that yesterday we were talking about yesterday, the last class. I mean, we were talking about the network simplification techniques, the basics. Okay, and we were talking about the registers in series, the registers in parallel, isn't it? And also we saw what if the resistors are in series and if the current flows there by connecting the voltage source there. Okay, and we saw that when resistors are same, the voltage drops are same. The current that is flowing through both the resistors is the same. Okay, now when R1 is greater than R2, B1 is greater than V2, V2. That means if resistor is greater, voltage drop across that also is also greater. So how to understand that? See here, those who have confusions regarding this. This is V is equal to IR, right? This is V is equal to IR. This is Ohm's law. Everybody understand that. Now, in this, what is constant? See, I is constant here. I is not changing. The current that is flowing through R1 and R2 are not changing. Okay, so since this I is a constant, okay, if R is greater, okay, V is also greater. This is the idea. So that's why, see, if R1 is greater than R2, if R1 is greater than R2, then V1 would also be greater than V2. That means greater is the resistance, greater is the drop across that. It's just that. So you need to look at which parameter is constant in this Ohm's law. Okay, and to maintain the equilibrium, the corresponding things happen. Similarly, if you come here, suppose there are parallel resistors. Okay, what is constant? Since R1 and R2 are in parallel and since the voltage that we have applied is also in parallel with these two, V1 is equal to V2 is equal to V. So that means it's a constant. V is not changing. V is a constant. Understand that? Now look at this. If V is a constant, if V is a constant, okay, V is equal to IR we are talking about, right? Here what's happening? V is happening to be a constant entity. It's not changing because the resistors are in parallel. So what happens if R is greater, R is increasing, suppose you say, which is not the case. Suppose R is greater means, suppose R is on the increasing side means the current has to be on the decreasing side. Get this point? That's why see, if R1 is equal to R2, I1 is equal to I2. But if R1 is greater than R2, I1 is less than I2. Okay, so this talks about that. So if V is a constant, for V to be the same, if R is increasing, I has to be decreasing. Or in other words, if I is increasing, R has to be decreasing. So this should happen for getting the constant V. That is why this is happening. Everybody understand that? Okay, so let's take an example. In the previous case, we saw that we obtained the equal values for V1 and V2, and the same V1 and V2 we obtained by using the voltage division rule. Understand that? See, this voltage division rule is shortcut to find out V1 and V2 when resistors are in series. Everybody is okay with this? Okay, so this voltage division rule is helpful when the resistors are in series because voltage, the applied voltage gets divided between these two resistors. Understand? So now what's happening here? Here in the series connection, the voltage was getting divided. In parallel connection, what is getting divided? The current is getting divided. Understand? So let's just try find out what is I1 and I2 here. Everybody's okay? Okay, let's try just find out I1 and I2. For example, let's take I'll take the same example with values. Fine. So let's say there is this R. Okay, there is another R. Okay. Now these two are parallel when you have terminals here. Okay. Let's say that this is our 2 ohms and this is our 4 ohms. Fine. And let's apply a voltage here. Okay. let's apply a voltage source. We have connected the voltage source, so how it is going to look like. So let's say this is our plus and minus. Sorry, this is minus. Fine. And this is the voltage applied. Let's say that the voltage applied is 10 volts. Fine. And the current is flowing here. The current is flowing here. And what happens to this current? What happens to this current? This current should get divided, right? As I told you, this current would get divided here. After it comes here, gets divided into two parts. One is I1 that flows through 2 ohms, or let's call this as I2 ohms. Okay, and let me call this as I4 ohms. There will not be any confusion. So this total I gets divided into two parts. One part is going into this 2 ohms, so that current I am calling as I2 ohms. The other current which is going into 4 ohms branch is called as I4 ohms. Fine. Now we need to calculate here. Find, there we had found V1 and V2, right? So here we shall find I2 ohms and what? I4 ohms. So this is what we have to do. So again, we need to have the total. Suppose what we need to know, to find out these two. Okay, I need to know this voltage is there, right? Okay, so if the voltage is connected in this, how it is connected? How it is connected? See, instead of writing it like this, we can, the same circuit can be written in this way also. I'm just talking about this as an example. This is series, this is one resistance. Okay, this is another resistance. Okay, and we have connected a voltage source in parallel. It is the same circuit, trying to show it in different way, that's it. Okay, this is 2 ohms, this is 4 ohms. Fine, so this is plus minus. If 10 volts is applied here, the same 10 volts would come across this also, because it is connected in parallel with this. Everybody should understand this. 10 volts is coming in parallel with both the resistors. Okay, so this is also 10 volts. Now here are the currents. This is I2 ohms and this is I4 ohms. So they have asked us to find out I2 ohms and 4 ohms. So we know that V is equal to IR. Fine. So this implies that, suppose we want I2 ohms, means what is V applied? V across that, V is equal to 10, right? 10. R is what? 2. So what is I2 ohms now? It is 5 amps. Everybody is okay with that? Now similarly, what is I4 ohms? I4 ohms is 10 volts is the voltage again, which is dropping across 4 ohms because it is connected in parallel. Okay, and the resistor is 4. So what would this be? It would be 2.5 amps. So this is how we can calculate the currents that is flowing through 2 ohms and 4 ohms. Now the same calculations, the same currents can be found by something called as current division rule. In the previous problem we used voltage division rule because we were talking about the resistors connected in series. Now we are talking about resistors connected in parallel, so the current is getting divided. See which current is getting divided? See, there was I flowing, right? This I is getting divided. What is this total I? What would this total I be? See, now we have found out that this I2 ohms and I4 ohms we have found out. What is I here? Anybody? What is this I flowing here? See here? This I total I is actually I 2 ohms plus I 4 ohms. Fine, I 2 ohms is the current flowing through 2 ohms is 5 amperes and current flowing through 4 ohms is 2.5 amperes. So the total current in the circuit is 7.5 amperes. This we saw there also. So this is 7.5. Okay. So let's say we're not only finding out I 2 ohms and I 5 ohms, I 4 ohms, but we are also finding out what total I and total I. Fine. Now, how can we check I 2 ohms and I 4 ohms here? Now we shall verify this. Okay. Verification using current division rule. Why current division rule? Now current is getting divided. Okay, let's write that now. Just a minute. Yeah, this using current division rule. What is current division rule telling us? Okay, so see here, current division rule tells us that this I 2 ohms, okay, is what? It's total current, or let's say this is I1 or I2. Okay, let's say this is total current into uh, the resistance of the other branch where I 2 ohms is flowing. See, I 2 ohms is flowing here. Okay, so you have to multiply the total current with the resistance of the other branch. What is resistance of the other branch? R, that is 4 ohms. Resistance of the other branch divided by what? R 4 ohms, okay, plus R 2 ohms. Let me just generalize this. Let me just generalize this by writing this. Okay, suppose what I'm saying is, suppose you have R1 and R2, fine, and you have voltage applied here, plus minus, you have V, you have I. Okay, so here is your I1 and here is your I2. If this is the case, okay, I1 is given by total current into resistance of the other branch. Resistance of the other branch is R2 divided by sum of the resistances. Is everybody okay with? So therefore, what is I 2 ohms now? Therefore, I 2 ohms is total current. Total current is 7.5 amps into resistance of the other branch, that is 4 ohms, divided by sum of the resistance, that is 2 plus 4. What is this? This has to be 5 amps. What is I2? I2 is total current into resistance of the other branch. Resistance of the other branch means where I2 is flowing except that which is the other branch, that resistance divided by sum of the resistances. Okay, so this implies that our I 4 ohms is what? Total current, okay, into resistance of the other branch divided by sum of the resistances, 2 plus 4. Okay, what is this supposed to be? This is supposed to be 2.5 amps. Do we get that? Yeah, getting it. Fine. So this is how we can check the things. Fine. So this is how we can verify. Verification using current division rule. So this voltage division rule is applied when resistors are in series. Current division rule is applied when resistors are in parallel. Everybody understand? Just note, 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 note one. What we have learned so far. Okay. Voltage division rule. Voltage division rule uh, is used when resistors are in series. Everybody is okay with that? What is the second thing that you have seen? Current division rule. Current division rule is used when resistors are in parallel. So this is what we have learned. So with these basics, this is just something that I just wanted to give you. You have seen all this. You were not very particular about current division rule and voltage division rule, but I'm very sure that you all are very aware of V is equal to IR. So using V is equal to IR, if you one is if two are known, the other unknown can easily be found out. Okay, so this is what I wanted to give as the introduction to basics. Now we shall go on with something very important that you will see throughout the what network theory subject, okay, and throughout this semester. Fine, so let's go on with that. That is KVL and KCL. What is KVL and KCL? They are Kirchoff's voltage law and Kirchoff's current law. Understand that? So let's learn this now. Now, everybody just look at this. Let's go with Kirchoff's voltage law, which is called as KVL. Fine. Now, let's consider a circuit diagram for that. Fine. What is the circuit diagram? This. Let's consider this. Okay. Let's consider the circuit diagram. You have R. Fine. You have another R here. Okay. Now, this is one voltage applied here, and there is another voltage applied. Let's say this is minus and plus. Okay, everybody just observe this. You have three resistors. Okay, let's call these resistors R1, R2, and R3. There are three resistors connected. Okay, so let me call this voltage as V1 and this as V2. Okay, now we have to apply the Kirchoff's voltage law. When we have to apply Kirchoff voltage law, what is the necessity of applying this is what we need to understand. Now, can anybody tell me how these R1, R2, R3 are connected? Anybody? Here also by using Kirchoff's current law or voltage law, we are trying to find out currents and voltages only. Okay, but we are talking about KVL here. Okay, to understand why we use KVLs and KCLs, okay, can anybody tell me how this R1, R2, R3 are connected? Anybody
Parallel.
interested? Which resistors are in parallel? There are three resistors. All the three resistors in parallel? Anybody? All the three resistors are in parallel there? No. Mushraf, can you unmute yourself? Mushraf Ali Khan. There's some people who don't unmute, right? When I ask them to. I'm making a note of all of them. Nitin didn't do that. Okay, Nikki, Pawan didn't do that in the last class. Okay, I'm making a note of all of them. You're not active. Prabhanjan, can you come on and tell me how R1, R2, R3 are connected? Prabhanjan. Prabhanjan there. Okay. Now look at this. Prabhanjan, I'll remember you, man. Okay. Those who are not connecting, I assume that they are not there. Fine. Now listen here. These R1, R2, R3, they are neither in series or nor in parallel. They are neither in series nor in parallel. These R1, R2, R3. Otherwise, we would have easily calculated, okay, the equivalent resistance between these two or these two terminals. That is not happening. This is called as star connection. This is called as star connection. Understand that? Now, when R1 and R2 and R3 are not there in series or parallel, these voltage loss and currents loss would be helpful to find out the currents and voltages. Get that point? Okay, what is the need now? When there are resistors neither in parallel nor in series, okay, then to find out the currents and voltages, we can come out with something called as KVLs and KCLs. Let's just see how we can apply the KVL here. Okay, first thing that you need to understand here before applying the KVL, see here, there are how many closed paths there? See, this is one closed path, this is one closed path, okay, this is one closed path, and there are three closed paths. And Kirchoff's voltage law says that it has to be applied along a closed path. There are three closed paths. So let's take, to refer to these closed paths, let's take this. Something happened there. Yeah. Yeah. Look at this. Now, let me take this. See here, this as A, B, C, D. Fine. Now, to refer to this closed paths, why didn't I name these two? Why didn't I name these 2 points? Because these 2 points are the same. This point is also D because this is connected to this. Okay. And this point is as good as this. So these are all point D's. Okay. But they are not the same points. A, B, C. Now there are how many closed paths? There are 3 closed paths I was telling. Yeah. Which are those closed paths? I'm just trying to give you the terminologies. Closed paths. Which are those closed paths? The first closed path is this, the outer one. A, B, C, D, A. So this is one closed path. See, A, B, C, D, A. This is one closed path. Which is the second closed path there? See here the second closed path. This is this A, B, D, A back. A, B, D, A. Fine. There is another closed path, that is B, C, D, B. B, C, D, B. Now, there is a difference between the first closed path and the next 2 closed path. The first closed path is called as loop, and The second and third closed paths are called as meshes. Can anybody make out the difference between the two? Can anybody make out the difference between the two? See here, there is A, B, C, D, A is there, right? So this is the outermost path. This is the outermost path. Okay, this outermost path has got two more closed paths within it. Okay, that is these two. This outermost closed path has got two more closed paths within it. So that's why it is called as loop. So loop is a closed path within which there can be more closed paths. But what's happening with this ABDB and BCDB? This ABDB is a closed path within which we don't have any other closed path. And BCDB is another closed path within which we again don't have any closed path. That means these are meshes. Meshes are the closed paths within which again you will not find any other closed path. Get that point? Okay. So loop is a closed path within which you will find some more closed paths. Okay. Mesh is a closed path within which you will not find any other closed path. And KVL can be applied to loop as well as mesh, which means that KVL is applied to any closed path. Fine. So let's mark some voltages here. Okay, in this is I've called as V1, right? Let me say this is VA and let me call this as VB because I'll be calling them as V1s now. So let's say this is V1. Don't bother about the polarities. Polarities I'm just taking some polarities randomly I'm taking plus minus. Okay, and this is V3. Now when we say voltage, we try to write the voltages along a closed path. Okay, so first let's apply close KVL to closed path ABCDB. Okay, what is that? See here, AB. Let's consider. I've not given the statement yet. I'll give you the statement. Okay, let's see this first. Consider A, B, D, A. Fine. And how many voltages are there? They are called as drops. V1, V3 are drops, and VA is the source, voltage source applied. So VA is the voltage applied. V1 and V3 are the voltage drops. So what is KVL telling you? KVL tells us that you have to take the algebraic sum of all these. Okay, it says take the algebraic sum of all the voltages. 10 minutes left. Let's take the statement. Let's take the statement and then let's say we shall consider this. Fine. Okay. Let's take the statement. Everybody take the statement. I'll come to that again. Statement. Take down this fast. Those who have not given the attendance can give the attendance. Okay, before the session is ended. Now KVL states that KVL states that algebraic sum of what did I write? Okay, algebraic sum of voltages along a closed path is 0. So this is what it is telling. Okay, now let's consider this. It's saying algebraic sum of all the voltages along a closed path is 0. Okay, so we have 3 closed paths, mind you. We'll take the algebraic sum of these. Why they are calling it as algebraic sum of, I'll explain you. Fine. Why they are calling it as algebraic sum of, I'll explain you. Okay, so let's consider a closed path. Consider closed path A, B, D, A. Now we have to move along the closed path. There are three closed paths. We have considered this closed path now. See here, we have considered this particular closed path. Fine. And when we are moving along, we have to move along in one particular direction. You can move in clockwise direction, or even you can move in anti-clockwise direction. Everybody should understand this because this is very important. Okay, so you have done this in PU. Okay, there are some people who move anti-clockwise, there are some people who can move clockwise, but let's all follow the same convention here. Okay, the rule that we are following is let's all move in the clockwise direction. This is clockwise direction, and when we are moving in clockwise direction, how many voltages you are coming across in this particular uh, closed path? There is VA, there is V1 and V3. Okay, and they're saying algebraic sum, we can add them up, but when we are adding them up, not all the voltages are positive voltages, or not all the voltages are negative voltages. There are some voltages positive, some voltages negative. Okay, so which voltage would be a negative voltage and which voltage would be a positive voltage is what we are learning now. Okay, everybody focus, very important thing. Okay, so let's all move in clockwise direction. So let's move in clockwise. When we are moving in clockwise direction, okay, the voltage that I'm coming across now is VA. Okay, see the pointer, I'm moving in clockwise direction. Okay, the first voltage I come across is VA. Now when I'm coming across VA, which sign of VA I'm approaching? See here, which sign of VA I'm approaching, I have to see. See, when I'm coming like this, when I approach VA, I'm approaching negative sign of VA. So which sign I approach, that sign should be attached to that particular voltage. That means the first voltage that I should consider in the algebraic sum is minus VA. Why it is minus VA, I've been telling you again and again. Okay, so when I'm approaching VA, you are getting minus sign first. That's why it is minus VA. Go further. We are finding B1 now. B1. So which sign of B1 we are coming across? We are coming across plus sign of B1. So let's have plus V1. Okay. Similarly, when we find V3, which sign of V3 we are coming across? First we are approaching positive sign of V3. So let's again attach plus sign to V3. So what's happening now? These two are plus, this is minus. Okay. So adding the negatives and positives is what is called as algebraic sum. Understand that? Why? What is algebraic sum? Algebraic sum, the term what is algebraic sum telling you? It is telling you that there are some positive voltages, there are some negative voltages. Negative voltages are considered negative and positive voltages considered positive. That means we are adding both positives and negatives. That's why it is called as the algebraic sum. So understand why it is called as the algebraic sum. The algebraic sum of the voltages along a close. How many voltages are there? 3 voltages. So algebraic sum of these 3 voltages is 0. See here. So this is what it is. Everybody understand? So similarly, can you move along the closed path BCDB? Can you move along the closed path BCDB? So this is VB. Can you apply KVL to the path BCDB? Everybody do that yourself and check whether you have learnt or not. KVL to BCDB. Write the KVL to this. How many voltages is there? 1, 2, 3. Again, so algebraic sum of these 3 voltages should give you 0. Can you write that yourselves fast? So there are 3 voltages. See, when I'm moving like this, I come across minus sign here. I come across minus sign. So which sign I have to consider? I have to say it as minus 3, minus V3 rather. Then comes this V2. When I'm moving like this in clockwise direction, I'm moving in clockwise direction, mind you. I come across plus sign of V2. So I'll attach plus sign to this V2. Okay, and when I'm moving in the clockwise direction, I approach minus sign of VB, so I'll consider that as minus VB. So this algebraic sum should give you 0. Okay, similarly, can you do this to the outermost path? I'll write that here so that it's visible, the circuit as well as the equation is visible. So this is one part. Okay, now let's apply KVL to A, B, C, D, A back. So this is outermost path. We can apply KVL to this also. Can you do that now? Do that yourselves, everybody. Apply KVL to ABC. Okay, what is that? See here. Let's start with this. This is when we come across like this. Now we are outermost path, mind you. This is outermost path. It's minus VA plus V1 plus V2 minus VB. So algebraic sum of these four voltages VA, V1, V2 and VB. V3 is not there in this path. V3 is not there in this path where we are moving. So V3 will not be coming. So VA would come, V1 would come, V2 would come and VB would come. But they would come with different signs. So how the signs need to be understood? You should understood by seeing which sign we are approaching first when we are moving in clockwise direction. Okay. So it's minus VA, okay, plus V1, fine, then plus V2 minus VB is equal to 0. So this is what KVL is telling us. Fine. Let's stop this here. Let's see the KCL in the next class. Okay. So if you have anything, you can ask me.